we're getting close to the end. We're in chapter 10, and then we've got 2 chapters after this, 11 and 12, which are both statistics. Today we're going to learn how to count. 1, 2, 3, that's it. Okay, a little bit more, but basically that's what today's about. So we had chapters 1 through 6 were for the midterm. If you still have anything to finish up on those, you can. Remember, you had actually 3 opportunities to take the midterm, so if you've used 2 of them, you still have a third one. If you wanted to try to improve your score, it takes the highest score of the 3. So those are still all available. But then since then, and then we've got the math of blank project. So be thinking about a topic. It doesn't take a lot of time, but it does take some thinking, and then a little bit of research, whatever you want, math of baseball, math of ice skating, math of building a rocket, so there's, you could just do a Google search on that, and you'll find lots of ideas. The goal is that you bring in 1 or 2, maybe 3 types of ideas, so you don't have to, go overboard, but how is math used in something that hopefully you enjoy doing, hopefully you are good at doing, something you're maybe an expert on. That'd be great. So there's those, and there's some examples in here of what people have done before. I had a group of students who were bartenders, so they did the math of bartending. It's kind of interesting. So you can look at what they've done just for examples, and we'll go through there. So then we did chapter 7, sets and Venn diagrams. Followed by probability, which we sometimes use the Venn diagrams in doing the probability problems. Last week we did advanced probability, which not too advanced, but a little. So chapters 8 and 9 pretty much went together. And then we're going to do the counting, which actually supplements 8 and 9 with probability. So you're going to see a couple of probability problems in here because it involves counting. And then we do a count. I think there's a lottery problem in here, which is kind of good for the the Powerball's now at what, $2.3 billion. I went and bought a few. Heck, it's got the same chance of winning if it's only 20, but heck, what could you do with a couple $1 billion? Or what is it? Yeah, it's over $2 billion, isn't it? If you take the 30-year payout. So anyway, we're going to see how we can actually calculate those probabilities, how they do them. Today, and then we've got just 1 more week, chapter 11, and then chapter 12 the following week. I think, let's see, next week we'll do 11. I can't remember. I think we do 12 during the week of Thanksgiving. That makes it. We come back a week after that, and then we're getting pretty ready to close things up. We'll take a final exam on 7 through 12. So again, the midterm stuff from before the midterm, it's not going to be on the final. The final will just be Venn diagrams forward. Venn diagrams, probability, and statistics. Some of this counting stuff will be there. Okay, and that's pretty much the course. Any questions as we go forward? And again, Thursdays will pretty much be for lab days, coming in, getting some assistance, or just having the opportunity to sit in a place where you have nothing else to do but math. Sometimes that helps. Okay, so we are going to, where is it? I thought I had it open. Oh, here it is. Okay, so let's larger. Oh, the other thing, as we get into this, come back, in chapter 10, there is a permutations and combinations calculator. I have it open for when we start working on the problems. This is going to help us. I'm going to show you the formula for and kind of how to do the calculations, but when you get to it, you just really have to decide whether it's called a permutation or combination. We'll talk about that. And you put the 2 numbers in here. It will carry out the formula. What I like about it is got the formula in here, and it will also do the calculation for you. Okay. What you're going to see is we could very quickly get very large numbers when we're counting. in this counting problem, and so that's why we use the formulas. Oh, where did it go? No, not there. There it is. Okay, so let's kind of go through this. We'll play it from the start. So counting methods, and it ties in with probability theory. We'll see, because what was probability? It was counting and then, a ratio of a number, the events we wanted in the top, the total number of events in the bottom, so it was a division. And this unit itself could actually be done either before or after. Since we're doing it after, it says chapter 11, but it's actually chapter 10 that we're in our book. This was from a different book. So fundamental counting principle. Okay, so we've got these objectives. So one of the things when we do, what we're looking at is number of options for something to happen. And so there's a group of certain number of items, and let me see, I forgot to get my other pen open. I think it's in, here we go. So when we're counting, we're going to see it actually involves multiplication. And to kind of highlight that a little bit, let's just sort of talk about math. So let me go back actually. Just some blank paper here. So we count, right? Counting. One, two, three, four, on and on, right? What are we doing when we do addition? Two things in one hand, three things in another. We put them together. How many do I have? 2 plus 3. When you first started doing addition, what did you do? You probably counted, right? 2, that's 5, because 1, 2, 3, 4, 5. So addition was just a way to count a little bit faster, so that we would recognize if I've got 2 and 3, I'm going to get 5. I don't actually have to count each one. So we would, I call addition counting with a memory. Okay. And I'll just abbreviate it that way. It made it faster. 10 plus 5. Oh, that's 15, because I could remember that instead of having to go and put them in a group and then count each one. 1, 2, 3, 4, 5, 6, 7, we got doing that. How about multiplication? What are we doing when we're doing multiplication? Think about sort of the simple part of the process. Yes, we memorized 2 times 3 is 6. That made it fast for us, but what's involved in multiplication? Couldn't we also do it as repeated addition? That it's sort of duplicating, so I could have 2 plus 2 plus 2, I get 6, or I could have 3 plus 2, or 3 plus 3, and I get 6, right? So multiplication is really repeated addition, and what is addition? Counting with a memory, right? So even multiplication, it involves counting. And what we're going to see is, if we're going to take advantage of that, we're going to use this multiplication principle to count things quicker. That's really all it is. So if you really think about it, all math is counting. It's just we get faster ways to do it, which then something we have a formula, but it's all just a matter of counting what do we have, right? And so we group them, and if you're a millionaire, you don't want to count each dollar to $1 million. You group them into bundles, or if you're a millionaire, you pay somebody else to count it, right, or something. But anyway, all this stuff we do in math is really just faster ways to count. But if you got down to it, if you had enough time, you could use counting to do all of the math, pretty much all the mathematics we do. Okay, so here we've got, we're going to talk about this principle is, and again, I don't read through all of this, but we have a young man who's getting dressed. He's got two different types of pants. He's got a blue jeans and a black jeans. So he's got two choices. And with each of those jeans, you know, to be fully dressed, I guess we got our pants on and we got a shirt on. And then he's got three different colored shirts. And so to think of how many different outfits could he have with this setup, well, there are two pants and there's another choice of shirts, so 2 times 3 gives us 6 different outfits, right? Oh, what's going on over here? Sorry about that. Maybe it needed us. I don't know what I said okay to. It's probably going to update now. Sorry about that. What did I do? It's going to restart. Okay. So anyway, 2 times 3 is 6. So and so whenever we have more than one choice, what we're going to see, we just need to, how many choices do I have at the first stage, how many at the second, maybe the third, then we just multiply all of those together. There's something going on. Let's just see if we can get the view board to work again. Okay, now we're back in business. Okay, so that's kind of the process we're going to do is, and you're going to see I'm going to put, I just figure out how many different choices, how many times do I have to make a decision. When I make each decision, how many choices are there? We multiply them all together, and that's the fastest way of counting that there is. Okay, so if we're at a restaurant, and I'll show you the way we do this. We've got the menu has 6 appetizers, 14 main courses. I kind of like dessert too, but they didn't give us that choice. So how I go to calculate this is I put a slot for each of the choices I'm going to make. So appetizers, and then the main, and we multiply them. So there are 6 choices of appetizers. There's 14 choices of main courses. So at this particular restaurant, I have 6 times 14, which is going to be 6 times 4 is 24. Carry the 2, 84 different meals I could have. So I could, if I'm a person, I'm a person who would probably order the same thing every time, but I've got other people who would probably wants to try it all. You could go out for 84 days in a row and get something different. At least these different combinations, right? With 6 appetizers and 14 mains. So 6 times 14, 84. Did I get, yeah, I got that right. Okay, so you kind of see, now we could also do a tree diagram, but when you have all those, you know, the first choice, you've got 6 different choices. From each of those 6 choices, you then have 14. So that's just the multiplication principle of counting. Okay, and then if we throw in, well, oh, we forgot about his shoes. He's got a pair of red shoes, a pair of black shoes, and so then we've got 2 pants, 3 shirts, 2 shoes. So we end up with 2 times 3 times 2. So now he has 12 different outfits, you know, and we can see down here with the tree diagram, you could actually list them out, and you can see, yeah, each one's a little different, you know. We got the blue shirts and the blue jeans, black shirts, you know. So this is what the types of things we're counting, and what we're going to quickly see is that there's a difference between if the order's important or if it's not important. Okay, ordering a meal, an appetizer comes first, the meal comes second, so there's order. You get dressed, there's implied order. You don't put your pants on your top half, it goes on the bottom. There's a place for each thing. So the shoes go on the feet. So there's an ordering involved in all of this. But we're going to see there's ones where you might not have to have order. So then, again here, just a simple thought. When you go to select your classes, you need to take 3 courses. So what we're going to do is we've got 1, 2, 3 courses to take, right? We're going to figure out how much of each. There's 8 sections of math. So for your math course, you have 8 choices. And again, you could imagine there's little lines coming off, 8 little lines. English, there's 5 choices. So 8 times 5, so far we've already got 40 different schedules we could get just from having 2 classes, a math class and an English class. But then we also need to take a humanities class. So there's 4 of those, and evidently they'd have to all be suitable. They'd have to be at times we could take them. And when we multiply this, what we see is these are all the different, how many different schedules we could have, right? And so ordering is important because it would buy time and such. So 8 times 5 is 40. 40 times 4 is 160 different schedules that we could actually work with. Okay. Now this becomes a little bit more daunting. You have to kind of notice that if you're the person making the schedule of classes, right? You've got 160 different options, and you got to make sure that they don't overlap. And so you could kind of see how whoever does the scheduling for a college, they got a lot to keep track of. They use to do the schedule? They do. They start saying, wow, how many, and how can we place these classes so we can give students the most options? Because if I put a class at the same time, you have to choose between one or the other, but you can't take both. But if I do it this way, then so yeah, they use this to see, wow. And then college might want to say, hey, we give you 160 different options to take 3 different classes. It makes it sound like you've got a lot of choices, right? Or anyway. And again, there's all these, they put them in here. So 160 different 3-course schedules. What I mean is so you see how we call this counting, but you definitely don't want to count 1, 2, 3, 4. This would take you a long time. Plus, trying to list all the different options out would be massive, right? If you try to miss what are all the possible schedules, you're going to have a list of 160 different schedules. That's a lot. So, of course, you schedule on one, you'll say, oh, I like this teacher over that teacher, and I don't like mornings, or I like evenings, whatever, so it narrows it down pretty good. If you take a multiple choice test, so if we have 10 questions, each question has 4 choices with 1 correct answer per question. If you select one of these 4 choices for each question, leave nothing blank, in how many ways can you answer the questions, right? So this is not how many ways can you get it completely right or something. So what we're thinking is, how many choices do we have? Well, each question is a choice. So we'd have 10 of them. I won't write them all out. For each question, how many choices do we have? 4. So I could choose any of those 4. And again, if I'm looking at how many different ways could I answer this, 4 times 4, each one has 4 choices. And so since I've got 10 choices, or 10 questions, right? What we're going to see is this type of a choice, I can write it as, since I've got 4, the same 4 for each of them, 4 to the 10th power. Okay, so we start to involve exponents. And again, another faster way of counting, rather than 4 times 4 times 4 times 4. We just take a calculator, 4 to the 10th power. And that's going to be an even larger number. So what is 4 to the 10th? 4 raised to the 10th power. That's 1,048,576 different ways of answering that same test, right? And again, I'll just I'll delete this, and then I'll let them kind of go with that. Okay, so a lot of different ways. Again, just counting. And what we're doing is we're building up these tools because, remember, probability, we need to know what's the total. And so sometimes we have to count what's the total possible ways. If I was randomly doing and I wanted to get them all correct, what would be my probability of getting this right? Since there are 1 million total, there's only going to be one way of getting 100% is if you choose the 10 correct answers, right? So there's one correct. So I have a 1 out of a million chance of getting 100% on this if I just randomly guessed. Okay. So if I got 100%, I either studied or my neighbor studied and I copied off of them. It's not, I don't recommend that, but by randomly guessing, it's not very likely you're going to get 100%, right? You could also do this, what would the chances of getting maybe 50% just by random guessing? Okay, then you would do more counting, and that's kind of what we're getting at. And you can see how the lottery, this ties us into lotteries. Okay. The other thing is we can use this for stuff like telephone numbers. And we might want to say, how many phone numbers are available with how it's set up. We're going to see license plates and stuff. So what we have to do is kind of see all the rules. So in the US, we have 3-digit area codes by a 7-digit number. So it's a 1, 2, 3, right? That's your area code. And then you've got a 3-digit number, and then you've got a 4-digit number, and that's every phone, so how many different phone numbers could we have? Well, the one thing we have to look is that there is a couple rules that you cannot start a number, that an area code cannot start with either 0 or 1, and also, 0 or 1. Also, the first digit of your, what do we call that? The local code cannot be 0 or 1, because 0, if you push that first, that gets you to the operator. 1 means you're going for long distance or something. So those are special codes. So how many choices of digits do we have for the first part of the area code? How much? 2 to 9, which is how many? 2, 3, 4, 5, 6, 7, 8, 9. It's actually 8. And that's one thing. So if you subtract them, you get 7. But since we're starting, we're counting with them. So 8. The next digit, we can use any of the, and we think we only have 9 numbers, right? 1 through 9. But 0 is a digit as well. So we actually have 10 digits that we can use. And so for each of these, we're going to get 10. For when we get back to the local code, we can't use 0 or 1, because if you're calling within the code, you don't need the area code. And then again, we've got 10, 10. All of these are 10s, right? And we just multiply them all together. Or we could say, well, there's 2 8s, so 8 to the second power. And then how many 10s are there? There's 1, 2, 3, 4, 5, 6, 7, 8. So that's 10 to the 8th power. Now, 10 to a power is real easy to calculate, because that means we've got 8 zeros on the end, right? 8 times 2 is 64, or not 8 times 2, 8 squared is 64, and then 10 to the 8th means we have 8 zeros. 4, 5, 6, 7, 8. Come back 3, come back 3, come back. So that's 6,400,000,000 phone numbers that we can make. Sounds like a lot, right? But 6 billion, how many of you have more than one phone number? You got a cell phone, maybe a home phone number, maybe a work number. Even sometime now, Apple Watches have their own phone number. Everything has it. So we could easily run out of phone. We're getting at a place where we could run out of phone numbers. with this current setup. I don't know if we've done that yet, but notice if we did it for the whole world this way, we definitely would. There's almost 10 billion people, I think. Look it up. I'm not quite sure. I know that one time there was 7 billion and it keeps rising. I just haven't looked recently. But so if we did this as a world, so what we have is each country has a country code, so that then they have all these numbers. And again, a business definitely needs more than one phone number. Some of them have hundreds of phone numbers, so you can see these numbers get used up pretty quick. But now we can count to 6 billion pretty quickly, right? I mean, don't want to do it one by one. And again, I'll just click here, and the PowerPoint walks you through these. And again, you do have access to this. This is in the, if you look at the overview for Chapter 10, I've got a copy of the PowerPoints in there if you want to download and look up any of the rules that we're doing. Okay, so nice way of talking. Now we're going to break this down into specifically permutations. Permutations, and there's this link to the calculator that I already have open. Let's go ahead and look at, that's the objectives. Okay, that's what we're going to do. What is a permutation? Permutation is choosing from a group of things, but you can only use one item once. And then we're putting them in some kind of arrangement. So we might take everyone in this class and maybe we'll make a committee that we're gonna complain to the college about something, and we'll choose 3 of us to go do that complaint, and we'll make one person the spokesperson, one the secretary, and one the moral support. Okay, so each person has an assignment, so there's an ordering, right? And each person can only have one item. So that's what a permutation is. We'll do a lot of this like books on a bookshelf, right? If I've got 7 books, I can only put one on the book, it can only be used once. Once I've used it, I can't use it again. Okay, so that's the idea of a permutation. So here we are with a book example. So we need to arrange 7 of our favorite books, on a small shelf. How many different ways can you arrange the books, assuming that the order of the books makes a difference to you? Yeah. And again, in a library especially, if you get the book out of order, you might never be able to find it, right? If there's a lot of books and somebody put it back in the wrong place, you won't know where to find it. So how do we do this one? Same thing we've been doing. Let's just maybe change color. We've got 7 books, so we're going to put down 7 slots because we have 7 choices, right? 1, 2, 3, 4, 5, 6, 7. How many books do we have to choose to put in the first slot? 7. We put a book, so we could choose any of the 7, right? So we have 7 choices. We put one of the books there. Now for the second slot, how many books do we have to choose from? But we put one in the first slot. So now we only have 6. So this is kind of like, okay, once I use it, it's done. So now I've got 6 choices. I choose one from the 6, put it there. Now in the third slot, I only have 5 choices. Put a book there. I'm down to 4 choices of books, 3 choices, 2 choices, and then there's the last book. It goes right here, so that's 1 choice. We multiply all of these because these could be different ways of doing it, right? Because for that first 7, I had 7 choices. I could put this book or that book or this book. So this actually gives us the number of arrangements of unique ways of putting the books on the shelf. Okay, and so we multiply these all together, 7 times 6 times 5 times 4 times 3 times 2 times 1. But you can see with this type of a problem, we're going to be doing this a lot, right? If I had 10 things, it'd be 10, 9, 8, 7, 6, 5, 4, 3. So in math, we come up with a special operation. We call this 7, and exclamation mark. So you've never seen this used in math before, have you? Unless you've seen this concept. It's called a factorial. So we read this as 7 factorial. And what that factorial means, it means do 7 times 6 times 5 times 4 times 3 times 2 times 1. a number of calculators do have a factorial button. It's usually hidden. I think this one has it, like I have to go to the math key. Let's see, where is it? And then over to probability. Yeah, there is a key that will actually do this, so I could put in, let's come back here, I do 7, I go to math, I get my key, and I do 7 factorial, and it tells me that this is 1048576, so 1,048,576 different arrangements. And again, I don't want to have to count them. That's a lot to count. I don't want to have to list them all. That's a lot to list. But if I did, I could do this. So if I wanted to change the order of my books every day, I could do it for 1,000,000 days and never repeat over 1,000,000 days and never repeat my ordering. This is showing you how much variety we can have in the world, really, with just 7 books. So we got a lot of different options here. Okay. Wait. What did I do? I got a different number. Oh, I never hit enter. That was that last calculation we did, 4 to the 10th. I better back up. Well, hopefully nobody wrote that down. Well, if you did, okay. It's actually still a lot, right? Not 1,000,000 days, but for 5,000 days, how many years is that? 5,000 divided by 365. That's a lot of years. About 15 years. Okay, so make sense? Okay, so yeah. And again, you could do this manually, just multiply them out. You could, but you could also use the factorial key. We're going to see this is going to build up to a formula for calculating probability or permutations, a specific order of books. Because maybe I only have 4 slots, and this is what it is. It's like a museum. They have a lot of pictures, but they only have so many spaces, and they could go through this permutation thing of, well, we want to make it look fresh, or like casinos. They don't want they want people to keep coming back. So one of the ways is they move the machines around to different orders, and then it feels like a different place. So we're going to look at permutations. Okay. And so here it is. It's just kind of doing it in if we had n items, which is a sort of a variable. It's n times n minus 1 because once we use one, notice we keep using. So we can make it, if we had 100 items, we could do 100 factorial, 100 times 99 times 98 times, so these numbers could become very large. One thing we have to understand, though, is if we have 0 items, we define that actually 0 factorial to be 1. Because if you have nothing, how many ways can you organize it? There's still one way to organize nothing. Don't think about that too long, but yeah, it's a blank space. That's still one way of organizing it. So that's why we call 0 factorial 1. 1 factorial is also 1. If I've got one thing, there's only one way to arrange it, right? If I've got 0 things, it's blank. So we call both of those are equal to 1. This is our permutation formula. And again, this is embedded in the calculator, so we're not going to have to use it. This is when we have something like a question where, I've got 7 books, but I want to put them on display, and I've only got 4 display places. Display slots. Okay, so let's kind of walk through this, and I'm going to show you how this is also, we're going to actually use the calculator. I'll show you how to use the formula if you want to, but again, we'll be able to use the calculator, or if you've got a TI-84, they've got this as a built-in feature. If you go to the math key and then over to probability, it's got it built in here too. So first, let's do this how we've been doing it. I've got 4 display slots, so I'll put those 4 slots. how many books can I choose for the first slot? Well, I've got 7 books. I put a book there. Now how many books do I have? 6. Put a book, got 5. Put a book, got 4. I still have 3 books left, but I don't have any place to display them, so I put them in the closet. So that I'm done counting my permutation here. It's 7 times 6 times 5 times 4. There's not a special way to calculate that, so I just have to kind of enter that in my calculator. 7 times 6 times 5 times 4 is 840, doing it sort of the long method. What we're going to see, though, is if your calculator has this sort of a key, or if you use the link I sent you, what we put in is N is the number of items, so that's 7. R is the number that we get to choose, or the number of slots, so that would be 4. So on our calculators, we would enter this as 7P4. Okay, and when we do that, we're going to get the number 840. And the calculator is going to do all the work for us. Because it's basically going to take 7 times 6 times 5 times 4. Let me come over here. Okay. That's what I don't like about this thing. The way I enter that in my permutation calculator, the amount in a set, and this has always got to be the larger, right? And if you get this backwards, you put the numbers in the wrong way, it'll figure it out. The number of slots we have is 4, and if I click on calculate, what you see is I get my 840 here, and it's showing me the formula it's using, but it's 840. That's if the order's important, because I'm arranging them, I'm displaying it. There's a first, a second, a third, a fourth book. We're going to talk about combinations because the calculator calculated both of these options. We'll talk about combinations in a moment. You see they're related to a permutation, but they're just, I'll go ahead and tell you, combination is just the order's not important. So this might be, I'm choosing 4 books to send to my friend. It doesn't matter the order I put them in the box. He's going to open them up, and it's which 4 does he get out of the 7, right? So that's what a combination is. It's the choices of a set of things, but the order's not important, because I throw them in a box, send them to him, he opens it up, it doesn't matter which order he puts them in. When I've got them on a display case, I've got a first, second, third, fourth book, order's important. So that's typically the hardest part of this section, is deciding is order important or not. If there's an order, if there's a first, second, third, order is important. Order is a consideration. If there's a different title, those kind of things. So we're gonna come back to that. Doing okay? Making sense? Okay. So let me just do this with the formula, and I'll show you how we actually end up with the same thing we just did. So what is n factorial? N factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's in the numerator. What is n minus 7? Or sorry, what is n minus r? Well, in this case, n is 7, r is 4. So we do the math first inside the parentheses. 7 minus 4 is 3. So then we've got 3 factorial. Well, what's 3 factorial? 3 times 2 times 1. And when we're multiplying and we have the same factor in the top and the bottom, what do we get to do? Three divided by 3 is 1. 2 divided by 2 is 1. 1 divided by 1 is 1. Notice we are left with the way I did it with the slots, 7 times 6 times 5 times 4. So what I found when I was doing this, I had a hard time using this formula, but as I just sort of played around, I said, you know, I never need to use the formula. I just think of my way. I've got 4 slots. I count them out. So I stopped using the formula. Even when I didn't have a calculator that would do all this stuff, but I would know, I've got 100 things and only 3 slots, 100 times 99 times 98. Okay, stop. And then that's all this formula is doing. Okay, but again, in this one, I'm going to encourage you to use the online calculator to do the calculations. Okay, so we'll walk through this kind of as if we were doing this. You and 19 of your friends have decided to form a business. The group needs to choose 3 officers: a CEO, an operating manager, and a treasurer. So if we choose 3 of these, is the order that we choose them in, is that going to be important? Is that going to make a difference? Well, if you're the CEO, is that better than being the operating manager? Or maybe, I don't know which one's better. One's maybe more work, but certainly the CEO probably has more power, and treasurer gets to deal with the money. They're different jobs, so yes, we would consider them each different. So there's 3 things, 3 slots. How many people are we choosing from? Be careful, it's not 19, it's 20. I went with 19 because I forgot to count myself. You and 19, so there's 20 people. So really this just breaks down to 20 times 19, because each time we make a choice we don't get to use it again, times 18. That's the answer there. Okay, and we could just calculate that by multiplying these 3, or we could, let's see if I can do this. We could come here and use our calculator and say we've got 20 items, we're going to choose 3 of them, and order is important, so we're going to use the permutation. 6,840 different executive boards we could come up with, with the different, that where the ordering's different. Now, one of them, the difference might be, the same CEO, the same operating manager, but with a different treasurer, right? So that all makes it different. But there's actually 6,840 different executive boards. And we're going to see if it was a committee where the order wasn't important. So if we do that, maybe we just want them to go study something and they don't have a position. We just need 3 people to go do some work. That's a committee. That's when we would use a combination. And what's happening here is we're dividing out the number of different ways something can be done. But what you're going to do is, as you go through the homework, you're going to come back and use this calculator each time, and you're just going to ask the question, is order important or not? So notice you'll get both answers. If you get it wrong the first time, it probably means, yeah, order was important and you didn't think it was, or the other way around. But the calculations are very similar. Okay. And again, you see they went through the long thing of using the formula, but not too long. They just said, okay, we don't have to worry about 17 on down. We just worry about these 3 slots, multiply it out, there's the 6,840. If you have a permutation calculator like we have, or handheld, you're able to put them in, and you just put 20p3, and that's a permutation. We're going to skip this. This is from this book had like duplicate items, like you had a arrangement of silverware with forks and knives, and how many did you have of each. But so it's still in here, but if you want to, you can take a look at it. It's a special thing, but we don't use this. I took for my master's work, I was working on a field that needed probability. We went through this, and we also didn't do these type of permutations with duplicate items. Okay. So now we're just going to talk about combinations, and we've done all the math for it already. The only difference between a permutation and a combination is order. One order is important, one is not. How about for a lottery ticket? Anyone bought a lottery ticket, like at least the way we're doing it, right? Say Powerball. Does the order the numbers get chosen from, is that important? It's not. If they choose 10 and you've got 10, it doesn't matter whether your 10 is in the first, whether the 10 was chosen first, second, or third, or fourth, or fifth. It's one of the balls. It's just how many balls you match, because there's one 10 in this bingo, in these balls that they're choosing from. So lotteries are actually combinations, they're not permutations. Most of them are. However, you could make them into a permutation. Okay, so we just need to be able to distinguish between the two. We'll solve some problems, and we'll be finished up here pretty quick. We'll go through the quiz to get the example homework problems. And so combination is when the order's not really important. So again, like if we had a committee, we've got Bob, Sally, Joe, and Fred. And let's say we need 2 people to go do something. If we choose Bob and Sally, is that the same thing as choosing Sally and Bob? If they're just going on some kind of a mission, they're both equally, there's no first or second person, then we would say order's not important. That's the same group. We're sending the same 2 people to go check the parking lot for something. Okay, so that's a combination. So that would be, usually the key word is that's a committee. Now, permutation, this might be different if the first person chosen is the president and the second person chosen is the vice president. That's a different dynamic, right? So permutation means order's important. So if it's like what we might call an executive committee, it will have a different dynamic if Bob's the head rather than if Sally. It will be different. So these are different. So we would count that as 2 items instead of just 1, is what happens. So the way we tell the difference, and that's what we want to, this one we're not going to calculate them, we're just going to say is whether it involves a permutation or a combination. 6 students are running for student government, president, vice president, treasurer. The student with the greatest number of votes becomes the president, the second highest, How many different outcomes are possible? So is this a permutation or a combination? Very good. It is a permutation. There's two ways to sort of see this, because they have titles. That's one indicator, and also because there's an ordering. The one with the most votes is going to go for president. So actually I don't have to write that, but it's a permutation. Order's important. Okay, pretty clear. 6 people are on a board of supervisors for your neighborhood park. A 30-person committee is needed to study the possibility of expanding the park. How many different committees? I clicked too fast. Can you see that is, the order's not important? There is not a leader of the committee. It's just a committee. So this is a combination. Okay, and just typically when you see a committee, but just watch for it, it might have an executive committee. An executive committee means there's a president, vice president, and so forth. Okay, and one way to kind of do this, if you put the letters A, B, C, D, and you're going to choose 3 of the letters, notice A, B, C, and A, C, B, those, if order's not important, those are the same 3 letters in the group, right? So we would, if for a combination, this only counts as all of these different options only count as 1, because they've got the same 3 letters. So notice it, if we've got 4, if we're going to choose 3 letters out of 4 items, with combinations there's only 4. But if it's a permutation where there's order's important, notice there's a lot more permutations. Okay, so that's the main thing. Permutations generally is going to give us a lot more options because order's important. Combinations, really the same problem as saying that the order, we're not considering order. And again, that's the idea of you shipping some books to your friend. doesn't matter the order you put them in the box, unless their friend is real picky or something. But yeah, OCD, yeah. And sometimes the number of possible combinations, and what you'll see is this formula is very similar to the permutation one. So there's the permutation right there. And what we're doing is we're dividing out the numbers of ways you can arrange the same items. Okay, so we divide that out to make it smaller, because those different ways of organizing it under a combination don't matter. Same 3 people are on the group, Bob, Sally, Fred, they go out, it doesn't matter, the order is not important. Their executive committee, it's going to make, the organization is going to make a difference. Okay. How many 3-person committees could be formed from 8 people? So we're selecting 3 people from 8. What we do is we use C instead of P. We have 8, and we're going to choose 3 from there. 8, choose 3. And again, we could go through the calculations, but that was part of the reason why I wanted to provide this. All we have to do is we've got 8. We're going to choose 3 of them. We calculate. What we do is we know we use the 56, the lesser one, because order's not important. If order were important, then we'd have 336 different choices to worry about, right? So once we determine order important or not, then we go. But you know, again, if you call the wrong one, and there's a few tricky ones we'll talk about, maybe in the homework or maybe before we get to it, but we just watch for that. Okay, so calculation's the same thing. Okay, the one I'm giving you, you don't have to. It'll calculate both of them for you, which is great. But you can also follow the calculations through, and you know, it's just sort of tedious. Okay, let's go through this one and see if order is important or not. In December 2011, the U.S. Senate consists of 51 Democrats, 47 Republicans, 2 independents. How many distinct 5-person committees can be formed if each committee must have 3 Democrats and 2 Republicans? So if they're on a committee, is order important? No, because we're not giving a head of the committee or anything. But this is a little different because we're choosing from 2 different groups, right? So there's 51 Democrats, so it's a combination. We've got 51 to choose from. How many are we going to choose? We're going to choose 3 of those because we're getting 3 Democrats, right? When it comes to the Republicans, we have 47 to choose from, and we're going to choose 2 of them. Now my question is what about the independents? They don't get chosen. Sometimes I get tired of politics, so I'm always independent. But, you know, and I think actually maybe we should have more independents. Maybe they would look for our interest better. But anyway, we calculate these 2 numbers and then we multiply by those. Because while order itself is not important, there is a difference between being a Democrat or a Republican. So, and you'll see some problems where you'll have to do this. You'll be basically choosing from 2 different groups. You figure those numbers and then you multiply. So the way I would go about doing this one is, let's see if I come here. We calculate them separately. So 51, it's the Democrats. We're going to choose 3 of them. Still 20,000 different choices, right? Because its order's not important. But that's 20,825. Let's see, let's go back to here. Oops. 20,000, what did I say? 20,825. Although the PowerPoint's going to do it for us, but I kind of like to work through it. It looks a little bit better this way. And then we have 47 choose 2 for the Republicans. And that's 1,081. Actually, I could write that while I'm still here. And so if I multiply those two numbers out, that gives me the total number of different types of committees. It's 2,251,1,825. Actually, it's 22 million. Get my commas in the right place. So 22 million different committees we could have. And they do the calculation there. Yeah, so they got the 20,825, which we did. Again, they used the formula. We just used the calculator. And then if we go to the next one, they got the 1,081 using the formula. We used the calculator. And then you multiply those two together, 22,511,825. Okay. Now, one of the applications I've seen of this, and I have a cousin who's an attorney, a lawyer, a criminal lawyer, and he came up with this idea. And he's a foreign. He was born outside of the U.S., so he's come here. And he says in many of his cases, if someone's foreign born, they have a higher. They charge them a higher bail because they think they're more of a flight risk that they'll run off. And what he was wanting to show is that using statistics, that they're no more likely to run than any others, and so why are you charging them higher? That's kind of what you could do here. Men and women pay period. You could say, well, there's randomly there's 22 million different things that could happen, and how many of these committees have a woman on it? Well, if it's only one or two, and there's potential for all these different ones, so you can, and we'll start doing that stuff sort of with the statistics. So that's where we use this. We use it in statistics, we use it in probability. Again, getting an idea of how many different things are possible, and then what's actually happening, so we could see if some bias is possibly going on. This is highly used in bias research. Okay, there's 22 million different committees, and your committees have all men. We should have a few women on it. So that's the end of the road for us. So what we're going to do is we'll take a look at the homework just to see if we've left anything out. We've got our calculator here. I think we generally have, let's see, homework quiz. Should be, let's see how many homework questions we have. We'll just start into it. 5 questions as usual. So we'll start with number 1. How many 5-letter passwords can be made using the letters A through Z? And again, this time we can't always use the calculator, but a lot of times it helps. If repetition of letters is allowed. So this is another thing that we never really went over. How many letters are in our alphabet? 26, yeah. We probably learned that in 2nd grade or 1st grade when we learned our ABCs and we forget it. But so there's 26. So if there's going to be 5-letter password, 1, 2, 3, 4, 5, we could have 26 letters here, 26 here, 26 here, right? So if there's 5, so that we'll calculate as 26 to the 5th power. Okay. So when we can repeat, it's not really a permutation, right? Because a permutation, we can only use it once. Repetition of letters is not allowed. Now this is a permutation. We could do it sort of in a similar way with the 5 slots and say 26 for the first, but once we use it, we can't reuse it. 25, 24, 23, and then 22. Or if we want to be even quicker, we just recognize, well, that's a permutation, so that's 26 permutate 5. I could use the calculator to do that. Okay, so permutation is you can't repeat. If I can repeat, then I'm going to use pretty much exponents. And let's go ahead and calculate that. 26 raised to the 5th power is a 11881376. That's 11 million. So a lot of passwords if you can repeat. If you can't repeat, then that's a 26. Choose 5. Oh, come over here. 26. So I can use this. I've got 26 letters to choose from. I'm going to choose 5 of them in a permutation where order is important because it is a password. You have to enter them in the right order, and we can't repeat. So that's 7,893,600. Still a lot, right? Still a lot. How do I get to this calculator? Canvas. So there's a link in the Chapter 10 module, and it's just right on the main, so it's on the front page. You'll see should be a little blue link. You just click on it. Question?
So that's a permutation, right?
That is a permutation. So we would use the bigger number here, 7,893,000. And I'm going to write that down here, 7,800,000.
So why is 5? Isn't it 4?
Did I read that wrong? It should be, I thought I said, yours might be 4, mine was 5, I think.
But it was 4.
5-letter password, a 5-letter password. Okay. And so 7,893,600. Let me check our answer. Got them right. Okay, does that make sense? So yeah, that and when you're taking the test, the final exam, you'll still have access to these. Just open them up and have them like at your tabs up here, so then you'll have all your calculators. I'll before we get there, remind me if I forget, but I'll put all the links for all the ones that we've been using on the final exam, so when you open it up, it just says open up all the different calculators that you might need. Okay, so that's a 6-digit PIN number is selected when what is the probability that there are no repeated digits. So here we are, this is a little bit of problem solving on top of the counting. 6-digit PIN number is selected. What is the probability that there are no repeated digits? Okay, so it's counting, right? So if the digits can be repeated, how do we calculate that? Well, actually, with repeated or not repeated, the total is how many digits do we have for a number? 0 to 9, which is actually 10 digits. 1, 2, 3, 4, 5, 6. So if we can repeat, it's 10 times 10 times 10, right? 10 to the 6th power, which that's an easy calculation. It's 1 with 6 zeros behind it. That's how the powers of 10 work, right? So that's a million different choices. But what if there is no repeated digits allowed? Well, that's a permutation, so we could do 10 permutate 6 because they're 6 digits. Or if you wanted to, you could go 10 times 9 times 8 times 7 times 6, 1, 2, 3, 4, 5, times 5. That would also give it to you. But what we want is the probability. So what we have to do is we take this number divided by 10 to the 6. Right? So did anyone calculate 10 permutate 6? 10. We're going to choose 6 of them. We're going to do a permutation. It's 151,120. Put that here. 151,200. Right, that's the number. And the total with repeating or not repeating is 1,000,000. So we divide those two. 151,200 divided by 1,000,000. 1, 2, 3. 1, 2, 3. I come up with 0.1512. So that's the probability, about a 15% probability, if you were to just randomly choose out of all the different choices. Does that make sense?
So it's over 1,000,000 because
10 to the 6th, because that's if we can repeat. It also includes not repeating, but and a probability we could list as a decimal. You probably write your answer in decimal form, rounded to the nearest thousandth. So I guess 3 thousandths is 3 places, so 0.151. We can check our answer.
So if mine's a 4-digit pin, I'd have to do 10 to the 4th. So then it'd be whatever my number is divided by 10,000.
Yes.
Okay.
Yes. So, yeah. And again, yeah, we want to see the methods, and this is gonna, your homework is going to be similar. Okay. Let's see, question 3. 3 letters are typed with repetition allowed. What is the probability that all 3 letters are vowels? So again, this probability is that we're counting 2 things. We always have to count the total. So 3 letters, repetitions allowed, 1, 2, 3. How many letters do we have in our alphabet? 26, 26, 26. So it's 26 to the 3rd power, right? If we want to count, that's our total. So that's going to be in the denominator of our probability. And then the event we're wanting is that all 3 will be vowels. Write your letters, answer as a percent. Now, if they're all going to be vowels, we're getting 3 letters, but repetition is allowed. How many vowels are there in our system? 5. So that's 5. Now, since we can still have repeats, that would be 5 times 5 times 5, or 5 to the 3rd, right?
So if mine says 5 letters are typed in, I go 5, 5, 5, 5, 5.
Right. So you'd have your 26 to the 5th, and then 5 to the 5th. Yeah. So yeah, the number of letters you're going to see, that's going to be your exponent when we have repeated, and then you just carry out the calculation. But notice it's just a little simpler. 5 raised to the 3rd power than having to either count it or write multiple. So if I calculate this in my calculator, and again, order of operations, this is going to be 0.007, and it wants it rounded to the nearest 100th of a percent. So, and it wants a percentage. So notice I have to, when I get my answer, I have to multiply by 100. So if I'm going to go to the 100th of a percent, that's a 10th of a percent. I better have an extra one here. I've got to have 4 digits here. Multiply by 100. I still get, actually, move the decimal over 2 places, I get 0.71%. Less than 1% chance of that happening. And again, they use this in games of chance, and also to see if things are really, if they say they're just by chance, but if, hey, I had a lot of codes coming up with all vowels, much more than 1%, I would say maybe something's wrong. So they use this in manufacturing too. You know, what is supposed to come out is this, and what's coming out is that, and this is a very rare thing, so maybe the machines are broken. You know, there's again a way of finding bias. We'd only expect this 0.71% of the time. If it's happening more often than that, maybe there's some bias. Again, it could. Remember, probability just says what's likely to happen, not what will happen. But in reality, when things are way off from what the probability should be, typically there's some kind of a bias going on, or some, you know, the machine needs to be fixed, whatever, you know. So far so good. Got 2 more questions. Okay, let's see how that, you know, it's using the counting to do probabilities. A lottery daily game. Player picks 4 numbers from 0 to 9 without repetition. How many different choices does the player have? So since we can't repeat, that's a permutation, right? And we're choosing 4 numbers. So again, we could do the slots. We have 10 digits to choose from, no special rules. So we have 10 for the first choice, but since we can't repeat, there's 9, there's 8, there's 7. So we could just multiply this, or we could recognize it as a permutation. We've got 10 digits to choose from. We're going to choose 4 of them. We could just calculate it with the calculator. 10 permutate 4. So we've got 10 on there already. Put in the 4, calculate it. That's 5,040. If order does not matter, because again, we can't repeat them, maybe the order that we chose, it doesn't matter. A lot of lotteries are that way. The cool thing is we just come back to our calculator. We've already got the calculation done for us, don't we? We just look at it as it's still 10 choosing 4, but now it's a combination, so there's 210. So which one's more likely to win? Well, if it's set up on a combination, you have a better chance of winning. Much better chance than if order matters. And again, it's just, in this case, it might just depend upon the rules. Okay, one more. Any questions so far? Doing good? Let's go to question 5. Wow. So this is with the deck of cards. And we've got 4 different, actually 4 problems within this one. But so a poker hand consists of 5 cards randomly dealt from a deck of 52 cards. The order of the cards does not matter. Determine the following probabilities for a 5-card poker hand. Write your answers in percent form, rounded to 4 decimal places. So the first thing we have to do is how many total poker hands are there possible? Well, how many cards are there?
52.
There's 52 cards. How many are going to get used in a hand. It's a 5-card hand, so there's 5 cards. And obviously, since you deal them out of the deck, you can't repeat a card. You can't get the Queen of Hearts twice. But since the order's not important, that's a combination rather than a permutation. So what we're going to do is we're going to calculate this. This is going to be the denominator of all our calculations, right? Because this is a total number of different hands. So that's going to be a 52. Choose 5, and it's a combination. So it's still 2,598,960 different hands. That's our total. So I'll write that down as the total. Okay, and now watch what ends up happening. We're going to use kind of this combination thing we did with when we were talking about the Democrats and the Republicans. Okay, determine the probability that exactly 4 of these cards are aces. Exactly 4 are aces. Okay, so how do we do that calculation? Well, the denominator will have and I'll write this out in sort of long form. It's going to have 52 cards. We're going to choose 5. So that's the total. That's the denominator. The numerator, we're going to choose exactly 4 aces. How many aces can we choose from? How many aces are in a deck of cards? 4. So that's a 4. The order's not important, so that's 4, choose 4. But we're not done yet. What about the last card? We actually have to count all the different hands that would have 4 aces, right? So 4 of them are aces. How many cards in a deck are not aces? 48. So that was a 52 minus 4. 48 are not aces. So from those 48 cards, we're going to choose 1. So this is, you can't just do 4, choose 4 and be done. This is a total number of ways. And so now we're ready to do the calculation. We've done the bottom part already. So that's 2,598,960. We're going to do 4, choose 4, and that might be kind of an interesting number, because you'll see whenever you have the same that this is, how many ways do you think this is going to give you? If it was a permutation, there'd be 24 ways to do that, because the order is important. But when order's not important, if you've got 4 and you're going to choose all 4, there's only one way to do that. So that's kind of cool. So in the numerator, right, we're going to have 1. Now 48, choose 1. How many? Can you just sort of guess how many that's going to be? Probably be right if you do. You've got 48 things and you can only choose 1 of them. There's actually 48 ways for that to happen. 48. Okay, so 1 times 48 in the numerator, and then we divide by 2.5 million. You'll see 48 divided by 2,598,960. They want them as a percentage, so then that, wait a minute, oh yeah. You'll get a number in your, if you're doing the calculator, you'll see e to the minus 5 probably. What that means is the number is so small, you have to move the decimal over 5 places. They want it as a percentage, so I'll write this out as I go, just so you can kind of see. So I got 1.846892603e to the minus 5. And what that means is that I need to move the decimal back 5 places. So it's a very, very small thing, but if I multiply by 100, right? Because I want to do now it gives me sort of a normal number. I get 0.001846. 8926. I'll write them all out. They want us to do it as a percent rounded to 4 decimal places, and you kind of see why that is. 1, 2, 3, 4. So if I'm going to round the 8, I look at the 4, so I'm going to leave it as an 8. This answer is 0.0018. Okay, very small percentage. It's not likely to get 4 aces. It can happen, but if you see somebody getting 4 aces a couple times in a row, you might think maybe they're doing something with this deck. Maybe they're, you wouldn't expect it to come up very often. Determine the probability that all 5 of these cards are spades. Okay, so what I'm going to do now, instead of actually going through the calculations, I'll set up the calculations. Okay, so all are spades. All 5 of these cards are spades. So how many spades are in a deck of cards? 13. 13 in any of the suits. So we do this sort of the same way. We're going to set it up with all the possibilities in the denominator. So out of 52 cards, we're going to choose 5. In the numerator, from 13 of the cards, which are spades, we're going to choose 5. Order's not important for either of these, and we've accounted for all 5 cards, so we don't have to do another calculation. Okay, so that'll give us, and then again, when we've got this, we multiply it by 100 to turn it into a percentage, because, right, they want the percent. So that's the calculation there. Determine the probability that exactly 4 of these cards are face cards. And again, since we're only counting 4, we have to count that the other card is not one of those. So we do the same thing. Go over here, change colors. So the denominator is always going to be 52, choose 5. 4 are face cards. How many face cards are in a deck of cards? There's 4 kings, 4 queens, 4 jacks. 4 times 4, those are all the face cards, so there's 12 face cards. So what we're going to do is from those 12 face cards, we're going to choose 4 of them. And then the other card, the last card, or maybe it's the first card, because order doesn't matter, right? The card that's not a face card is going to get chosen from the ones that are not face cards. So since there are 52 cards, 12 are face cards, there are 40 that are not face cards. Okay, so that's what we're choosing from. So again, you'll calculate 12, choose 4, and then you'll multiply it by 40, choose 1, and then you'll divide it by 52, choose 5. So you kind of, like we did up here, get all the numbers. And again, since they want the percentage, you multiply by 100 with all of these. Okay, determine the probability exactly 2 aces and 2 kings. And again, the denominator is always the same in all of these because that's the total number of different hands we could have. 2 aces, so there are 4 aces, and from those 4 aces we're going to choose 2. There's 4 kings, so for those 4 kings we're going to choose 2. And don't forget the last card, or maybe it's the first card, the other card. There's 5 cards, right? So we've counted aces and kings. This last card is not an ace or a king, so that's 52 minus 8, right? So what's 52 minus 8? Gives us 46. So the last one will get 46, and from that we'll choose 1. So notice that whenever we set this up, that the number we're choosing is always going to be 5. 2 plus 2 plus 1 is 5. And what we're choosing from is always a total of 52. 4 plus 4 plus 46 gives us 52. Okay, so again, we calculate each of these separately and then multiply them out. And finally, multiply by 100 to turn them into a percentage. And then we've got this last one. Probability of getting exactly one jack. So we'll do that. Again, getting one jack, there are 4 jacks. We're going to choose one of them. Total is going to be 52, choose 5. And then for the other cards in this hand that are not a jack, how many do we get to choose from? Well, 52 minus 4, right? So there's going to be 48 cards that are not jacks, and from those we need to choose 4 of them. We don't care which one. This will be just, we'll get one jack and could have any of the others. So again, we do this calculation. 4 choose 1 times 48 choose 4 divided by 52 choose 5, and then we multiply the whole thing by 100 to turn it into a percentage and put that answer in here. Now, folks that are good at poker, they have these, they don't necessarily calculate each of these individually, but they have an idea of the likelihood of something like 4 aces of happening. You know, what's the possibility of this probability that all cards are spades? That's what's called a flush, I think. It's been a while since I played poker. Anyone else play poker? No? A flush is that, yeah, you got all of the same suit. Yeah. It's been a lot. It's one of those kids. We played this as kids, and then anyway, then you can see what the probability of a particular one. But again, if you got for all spades, then you can multiply that by 4, because it could be they're all spades. A flush could be any suit, but that's the probability of getting all from the same. So it kind of gets you to see your calculations. And of course, being a good poker player is more about having the poker face and betting, and you know, because you got it's more psychology than it is mathematics. But anyway. Although at ASU, one of my colleagues I work with, if you're interested, I can send you the link to the YouTube link. He was in this, I don't know, if you don't play poker, you probably don't watch it. They have a celebrity poker tour. He was actually on TV. He won like $250,000 on a poker tournament. And he's playing these guys who were millionaires and stuff, and they kept on going, yeah, you're just a math teacher. Well, he was the one that beat them all, so he knew his probabilities, but he knew how to bluff. So anyway, that's what we use this stuff for. Any questions, or you want to go through any of these? We okay with the sort of basic setup? Okay, and you just put them in and try them out. Remember, you only need 70%. Yeah, you got to play, yeah. And again, come back to this permutation calculator. One thing I will tell you though, I think it's in here, but it might be wrong. It's one that always threw me. It's like you have 20 songs on your iPod, or you know, I don't know if they have those anymore, and you want to do a playlist of 7 songs. The thing is a playlist of songs, is that a permutation or is that a combination? A playlist. There's a first song, a second song. Now you may say, well, that's not important. I don't care the order, because you put it on, maybe you put your playlist on with the shuffle, so you don't really care the order. Maybe you could say that. But if we have a playlist, typically there is a first, second, third. So the questions in here, that's the one that always threw me. I would say it was a combination, because yeah, I do it on shuffle. They say it's important because you've got a first song, second song, third song. So like at a concert, yeah, it is important, because and if you're a DJ, my DJs in the classroom, because we actually are one of the few, maybe the only school in the country that has a DJ degree in being a DJ here. And if you're a DJ, you notice that when you want to get a crowd excited, you play your songs in a certain order, and you get the beat to go up like this. If you want to bring them back down, you have to go the other way, but the order you play things in is important. So that's, again, give it a try. Let us know. I'll be here Thursday, and then we're going to, some of this will apply into statistics, but this kind of wraps up our probability for the most part. And that's all I got for today.